And finally, I'd like to invite Chris Salvino from Lunar Helium-3 Mining. Thank you.
Well, good morning, and now for something a little bit different. I'm going to be talking about powering the next era of nuclear fusion and quantum computing by something that a couple years ago would have been considered a pipe dream, and that's Lunar Helium-3. So the singular focus of our company is to develop the technology to extract helium-3 from the moon for use cases of fusion and quantum computing. We're going to succeed through our intellectual property, partnerships, and the sole focus of this company is to extract helium-3, nothing else. I only put my background up here in context of learning about helium-3 through geology, but when I was at ASU learning about geology, I realized there was not enough about the mining process or the equipment that could be used. So I went off and got additional degrees in mining plus aerospace engineering to understand the isotope better. As many know, that helium-3 comes from the sun, travels in the solar wind. On Earth, it's captured in our atmosphere, so it's unusable. But on the moon, it's been baked into the regolith for billions of years. There's an estimated 1 million tons on the moon, enough to power fusion for a couple hundred years. The United States is going back to the moon as a cost center. They're going to go do research at the South Pole looking for water and ice, which we already know is there. I would hypothesize and promote that there's one revenue generator, a sole revenue generator, and that's the extraction of helium-3 from the lunar surface. We're going to go through 2 use cases. I'm not here to talk about fusion because that's your area of expertise. I want to talk about the fuel. So I put a slide up here in which it compares fusion, which we call 1.0 tritium, versus helium-3, which is 2.0. If you had helium-3, there's significant advantages. We believe this would be the world's first true green energy source. It has no storage for byproducts. It's relatively safe. And ironically, when you go to mine lithium and convert it to tritium, there is a carbon footprint that's markedly less, even if it's offset by rocket fuel. From a broad stroke point of view, if all the world was powered by fusion with helium-3, you would need about 570 metric tons per year of helium-3. Let's switch over to the second use case of quantum computing. Many of you may be familiar with this, but for those of you that are not, this is still experimental, but it's rapidly advancing. It's wickedly fast. When quantum computing comes online in a big way, it's going to be very useful, from cryptography, probably discover drugs, potentially cure some types of cancer, and politically, whichever country has this first may have some information dominance. Without helium-3, you cannot cool down the quantum computers close to absolute zero, which is where they operate efficiently. Broad stroke numbers, these are rough. Each quantum computer is going to need about 1 to 10 liters of liquid helium-3 in conjunction with helium-4. No one knows exactly how many there will be in 10 years or 15 years. We took a broad estimate of 10,000 quantum computers in 15 years. The helium demand for this would be about 4 metric tons. Okay, now don't yell at me about these numbers. This is broad revenue projections based on today's dollars at about $30,000 a gram. And by the way, tritium is more expensive, as you probably know. But if you looked at fusion, if the world used helium-3 for fusion at 570 metric tons, we're talking trillions of dollars of revenue per year. Quantum computing is smaller, but still not insignificant. Sourcing, helium-3 up until now has come from weapons production, and the supply is dwindling. You cannot mine it. There's been discussions about production, but scaling of that appears to be difficult. Therefore, the most likely source for large-scale quantities of helium-3 is on the surface of the moon. From a competitive landscape point of view, if you look off to the right first, the TRL level for pretty much everybody is probably between 1 and 3, so it's early stage. At the top left, China has brought back samples just like Apollo did, but they've actually come out and promoted the fact that they're going to go to the surface of the moon to mine helium-3. and they're going to have astronauts on the surface in 2030. India's talked about this. Ironically, the United States does not have a public position on this. They're still planning to go into the South Pole to look for water and rocks. There's private companies that have talked about this, including ours. We believe our competitive advantage, and I'll talk about a little bit of this coming up, is to work with the environment of the moon and not against it. We'll talk about efficiency using a low-energy approach, and durability using a mining approach that has minimal moving parts. This is the most important slide up here. This is the ROI, or the positive return on investment. This is how this is going to happen, is when these three things come together. You guys are working on the bottom left. Fusion's not that far out anymore. The top, the cost of transportation going into space is dropping, and then the bottom right is in red for a reason. You cannot go to the moon and use Earth-based mining techniques. You have to base your mining techniques on the Earth's or the lunar environment. Some people have proposed this type of vehicle is the way to mine the moon. There's a lot of moving parts here. There's a bucket wheel in the front that grinds up the regolith and drives into the rover, extracts helium-3 and spits out the tailings. Keep that in mind as we talk about the next two slides. So there's two major challenges to mine the moon, at least. I only have time to cover two. First one is the concentration of helium-3. Yes, there's 1 million tons, but it's in low concentration, roughly 1 part per billion. If you used Earth-based mining techniques, the energy formula does not equate. So we have come up with a low-energy extraction process designed for lunar conditions. The second challenge is some things we learned from the past, from the Apollo astronauts. This lunar dust is not Earth-based dust. It's sharp and spickly, it's high in silica, it's charged and magnetized, so it's going to cling to everything and destroy equipment. In fact, it's kind of for fun, but it's also kind of scary. If you look back at the last Apollo mission in 1972, just 22 hours on the surface, this lunar dust basically did a lot of damage, including almost eroding through Harrison Schmidt's foot. So our solution is to come up with a mining process, which we have, which has minimal moving parts. When we formed our company a couple of years ago, the whole idea was to take a blank sheet of paper, a systems engineering approach, first principles, and try to figure out how to mine the moon and work within the environment of the moon itself. Our singular focus is, our only focus is extraction of helium-3 and returning it back to Earth. If you look at the graphic, we fall within 5 steps and we don't go outside the zone, from targeting the surface and the subsurface, through heating, through vaporization, directing gases, separating gases, and concentrating them down. That's our sweet spot. This has resulted in a patent portfolio that's fairly extensive for only been around for a year and a half. We have US patents that are issued, pending, and international patents have been filed. And our final slide is our business strategy. Roughly, from an idea stage to commercialization, we think there's 3 major stages. Phase 1 was a foundational development, which we've completed. That was basically trying to come up with a process with a TRL level of 1 to 2, which is completed and patented. The second stage is now where we're looking for investors to scale up. The second phase will probably take 2 or 3 or 4 years to scale up our IP, to go into the lab. And finally, the final stage towards commercialization will be a very, very big undertaking. This will probably be done through partnerships, direct operations, through acquisition of capital, or an acquisition of the company as itself. Thank you for your time, and I hope I finished under 10 minutes.
Thank you very much. So now we're going to take some questions. So if I could invite all the previous speakers to come up here on stage. Chris, please. All right, please take a seat. I'm going to put this one here. Thank you. So interesting presentations from all of you. We've got some questions here on Slido. If anyone else wants to ask any, please do go onto the app and add your questions in. Right, let's start with Enable Fusion. Is Korea's role in fusion A, making a fusion machine, or B, making components and systems for fusion, or C, supporting with science and engineering? Do one. Is Korea's role in fusion making a fusion machine, making components and systems for fusion, or supporting with the science and engineering?
Oh, it's depending on the situations, okay? We are actually making the fusion machines, something like TF coils, vacuum vessels, and the cryostat, something like that. But we also making fusion component. But as far as HTS is concerned, the fusion AI is concerned, we are doing some supporting on science and engineering too.
Thank you. I've got a question for you, Chris. Does the need for how much does fusion or like commercializing fusion affect your business? And is it just from fusion energy and the demand side, or could fusion propulsion actually help your business as well?
I think propulsion would also be a key user. We actually think quantum computing is going to be the first driver. It's a smaller amount, but it's a strategic thing for governments. So if we have quantum computing first, we believe that smaller volume will get quantum computing up. We will learn how to scale up, and that might then lead into fusion down the line.
Thank you. So a question for X-Fusion. How significant is the laser cutting business, and would you spin it off before before it becomes a distraction to the objective of fusion power?
Yeah, so actually we have a unique technology of the accurately controlling of the laser system using our deformer mirror and the steering mirror. So we sell this product for some of the automobile company or space industry, and also heavy industry in Japan, making the laser cutting machine. So I mean, this is one of the option of our company, because our startups need the revenue from someone, and it is also important things like it is kind of improvement of our unique skill or unique technology. So that's why some of the application is important for our company.
Thank you. And Hafiz, what is the key risk on your path to commercialization, and by when do you expect to retire it?
One of the reasons is that we are trying to test the idea on the existing machine is to eliminate all the risks. So far, there is no risk other than electrodes designed so it can last multiple shots and high rep rate. And we are working on that technology, and we are very close. And this year, our test on L3 Harris Quad Eagle will demonstrate scientific break-even, hopefully, and once we have enough funding to build our own machine, can demonstrate the net gain in the next couple of years. So I don't see any risk other than some technical issues.
Thank you. And Chris, how many people will need to be on the moon, and for how long to make this work?
Well, that's a good question. Part of it goes back down to one of my points I brought up. Most of this is going to be autonomous, but we're going to need people to repair things. And if you have a system that's very complex with a lot of moving parts, you're going to need a lot more people. If you can use a system with very low moving parts, the amount of people will be markedly less. Maybe 5, 6 people on the moon at the initial stage to repair a few of the rovers, to extract things, but I think it's going to come down to the one point. The regolith is going to damage tons of equipment, so you got to respect that part.
And what's the status of your rover development? Are you developing it on your own, or do you already have a concept?
So that's another great question. Our focus has been on what's underneath the rover, sort of like when Amazon orders some trucks, they don't build them themselves. We are going to focus on what's underneath the chassis. We plan on partnering with rover companies, EVA suit companies, transportation companies, and bring a team together.
Thank you. And how much will it cost to make the L3 mining operational? What's the key milestone in proving it's feasible, and what will it cost you to get to that point?
The first part, I think, is still a little bit iffy, probably in a couple $100 million range. The second part's is interesting too. It's not going to take a lot to go into a lab with simulated regolith, injecting helium-3, and using our system to show that it actually works. What you can't simulate is 1/6 gravity and some of the environmental factors. You're going to have to go to the moon to truth that out. But it can be started in the lab relatively inexpensively.
And no one's been on the moon for several decades now, so when do you expect that you could actually start sending people to the moon, and how long would they need to stay there?
Well, the Americans are going to be there. They were supposed to be there this year. Now they're expecting to be there in 2026 with the Artemis program. And as I brought up, we're trying to change, our small little company's trying to change the trajectory of NASA, which is to go to the South Pole to find water in a crater and measure some rocks, which geologists know there's ice and water there. The trajectory really should be strategic, and it's this particular resource. So we have to change NASA's mindset, but there will be American astronauts on there soon. But China is right in the hunt. They expect to be on the moon in 2030, maybe 2029.
Mm-hmm. Thank you. And going over back to Duan about the Enable Fusion, where did the inspiration come from to start Enable Fusion?
Everybody considers generative AI will expedite the fusion development very well, okay? And using generative AIs, your simulation time can be reduced to something like 10 to the fifth degree. So usually with the supercomputers, it takes about 100 seconds for simulation, but it takes milliseconds for when I'm using AIs. So with using AIs, you can do real, not physically perfect tokamaks, but engineering perfect tokamaks, you can learn it on. So that's what we are working on, software-defined fusions.
Mm-hmm. Okay, thank you. And making everything faster. Well, that's we've come to time here, but thank you all of you for your enlightening presentations and for the questions. Now we've got a short comfort break before we kick off today's program. So please go refill your coffee, but come straight back in because we'll be starting again in just a few minutes. Thank you again. invite you up to come and say a few words. Yeah, you come up. I'll hover here awkwardly in the background, and you two can take the podium. Is that all right? Yeah, and if you start going on, I'll prod you with my pen. And